So welcome to this pre-recording of a lecture on linear algebra within the context of symbolic computation. So this lecture is intended not to teach linear algebra, but mainly to give an overview of what is available within the context of symbolic computation, and in particular within the software system SageMath. So with the slides, I want to give some focus and overview. Um, we distinguish between linear algebra where division is possible, and we can also do linear algebra without any division. So we first consider matrices over number fields. Okay, so linear algebra works with matrices and vectors. So the standard format to write a linear system, here an example symbolically, we have two equations, two unknowns. We have coefficients, so the unknowns are x1 and x2. We collect them in a vector x, and also the coefficients are separated. The coefficients in the matrix, which will be the matrix A, the coefficients are separated from the unknown x values. Typically, the matrix A and B are given, and then we want to solve for x. Okay, so how the solving works. We apply some factorizations. So here are four of the most important factorizations. So again, within symbolic computation, we can interpret these factorizations as bringing the matrix into a simpler form or a normal form. There are four different types of normal forms. Well, two main types with four factorizations. So the first two normal forms are triangular. So we either do a row reduction and compute an LU factorization, where the matrix A can be written as a product of a lower triangular and an upper triangular matrix. The lower triangular matrix is typically invertible with multipliers, and one can also see this as an operator, what you apply on the matrix A. So very much related to the LU factorization is the QR factorization, related in the sense that it also reduces the matrix to an upper triangular form, but it is applicable for matrices with more rows than columns, for overdetermined linear systems. It also fits well within the context of optimization. So we are going to minimize the residual, and we are going to apply orthogonal transformations. So orthogonal matrices are very nice matrices. If you transpose them, the columns become rows, rows become columns, then the transpose is the inverse of the matrix. So these are the first two matrix factorizations, reduce the matrix to a triangular form. Then we have the reductions to diagonal form. And both reductions to diagonal form, they do have geometric interpretations. So when we compute the eigenvalues and the eigenvectors, we compute those directions of the space in which the matrix stretches the unit vectors according to the size of the eigenvalues. Matrix norms are defined by looking at the largest eigenvalue. So we can collect all the eigenvalues in a diagonal matrix, and then the eigenvectors, when stored in the columns of a matrix, here denoted by V, they serve as a diagonalization operator. So we can see this eigenvalue decomposition also as a rewriting of the original matrix into a more convenient form of the matrix, and that matrix kind of especially also the eigenvalues kind of characterize the geometric properties of that matrix. So the last decomposition, so the singular value decomposition, also has a geometric meaning. Often it's a diagonal transformation, but now using orthogonal matrices. So in a way, it generalizes the QR factorization. So in a lot of applications, you may have matrices that are close to being singular, in the sense that there is not a unique solution when you consider a linear system with that coefficient matrix. Then one can still solve it by projecting to the nearest singular matrix, and that is done with the singular value decomposition. So in a computer algebra system like SageMath, these 4 factorizations are available, and we typically start with, we work over fields, and the default field is the field of rational numbers. We will see that keeping working with the rationals leads to the expression swell. So in particular, the numbers are getting quite larger. The other problem is that we need to, when we compute the eigenvalues, we actually are solving roots of a polynomial equation. And then we go to a proper field extension using the field QQ bar that we have seen. The QR and the singular value decomposition, for that we need to convert to the complex double field. So we were working with fields, but it depends which field that our matrix is represented in, depending on what we want to compute. Okay, so fields where the division works. In a ring, such like working with integers, if you start dividing them, you end up with rational numbers, which may be perfectly fine, but sometimes we don't want this. We can triangulate, we can bring a matrix into triangular form without divisions. And greatest common divisors are an important tool there. Here I will illustrate this with a very simple example. We can introduce zeros by unimodular coordinate transformations. So here on the example, we compute the greatest common divisor, the extended greatest common divisor. So any greatest common divisor can be written as the linear combination of the inputs. So here the greatest common divisor of these two numbers is 2. And there are 2 cofactors that allow us to express the greatest common divisor as a linear combination of the input numbers. These cofactors are interesting to define the unimodular coordinate transformation. So in order to introduce a 0, we are going to use on the second row here, so we want a 0 on the second row. So we introduce, and I see now that there is a sign error, so I forgot a negative. So if there is a negative in front of the first number here, then when you do the matrix vector product, the second element will be 0. And the first element will be the greatest common divisor by the property of these cofactors. So modulo this sign error here, I hope you get the idea. So with these unimodular coordinate transformations, we can selectively introduce zeros, and the unimodular coordinate transformations are invertible. So if you do the coordinate transformations on the left, you can accumulate all of them to actually reduce the matrix to also see this as a factorization of the matrix. So this will lead to the Hermite normal form, as I hope to illustrate in the second part of this lecture. So why is this so important? Well, in the previous lecture, I hinted or I mentioned the properties of the Gröbner basis to solve polynomial systems. So with resultants, and this relates to doing linear algebra without divisions, working with polynomials is interesting, very similar to working with the integers. One can multiply, but one cannot divide. The resultants, to make a resultant, you view your polynomials as polynomials in one variable, and then you ask for a condition on the coefficients of these polynomials in the leading variable. So here we look at polynomials in x with rational coefficients as polynomials in y. So this notation here, q of y, means that we see the polynomials as polynomials in x, and then we ask for the condition on the coefficients of these polynomials so that there is a common factor. And that can be expressed as a polynomial in y. And that polynomial will vanish if and only if there is a common root of these two polynomials. This relates to linear algebra because one can formulate this as a matrix, and then computing the determinant of this matrix defines the resultants. So one reduces this system of two equations and two unknowns to a triangular form. And that's an alternative to constructing a Gröbner basis with a lexicographical order. So this is also to indicate why linear algebra is important to solve symbolic problems. Okay, so these are the slides. So let me now pivot away from the slides and go to SageMath. So I have a Jupyter notebook prepared. So the purpose of this lecture is not to introduce linear algebra from scratch, but to give an overview of the capabilities in linear in a symbolic computing package. So so this is already lecture 30. So we do linear algebra, and what this actually means, doing linear algebra, is to solve systems of linear equations. So this is the notebook that I'm making with the recording. So systems of linear equations are defined by matrices. So let us make a 3 by 3 random rational coefficient matrix. So I will call this matrix A, and that will be our running example. So it's over the rationals. and I want to give the bound on the numerator and on the denominator. So I want that the rational numbers are actually not larger than 100. So here is my coefficient matrix. I can use the same syntax for the right hand side vector. So also here the bound on the denominator and the numerator should not exceed 100. So this defines a linear system. So if you ever have to solve a linear system and you're not yet disconnecting, well, here is the backslash operator. Extremely useful to compute solutions. What I want to indicate here, so first of all, why is this a solution? Well, let me compute the residual vector. So b minus a times x is what I call the residual vector, and that vector is 0. So here you see our first calculation. It's an exact calculation over the rational numbers. What you observe is that I was cautious not to generate systems, a linear system where the coefficients were kind of large. Well, what I got out of this were numbers that were already quite huge. So solving with exact arithmetic, exact rational arithmetic goes quick, but one has to be mindful of the expressions well. So this is another instance where we, in this course, observe the expressions well. So we started with modest rational numbers and ended up with rather large numbers in the solution X. So that's why one has to be a bit cautious. Before I go to the matrix factorization, so this was a random matrix. Often matrices are defined by formulas. So we can construct, so here is an exercise which I will solve, construct the 5 by 5 Hilbert matrix, where the ijth entry is defined by 1 over I plus j for I and j starting from 1. So here you will see what is the problem. The matrices, the matrices actually in SageMath follows Python. The matrices actually start from 0. So that is a problem if I'm applying this formula. So the function that I will define will be a function that takes on input 2 indices, and it has to take the inverse of I and plus j, but for the indices, for the matrices, they will start at 0. And I do not want to divide by 0. So this is a Python function where the first element h00 will be 1/2. So my Hilbert matrix is now defined as a matrix over the rational numbers, where I provide the h as a last element. So I indicate that this is a matrix of rational elements. It's a 5 by 5 matrix. So if you like a 5 by 4 matrix, so then one needs to provide a second argument. So by default, if there's only one dimension given, then the matrix is square. The second optional argument is the number of columns. Okay, so I will later indicate, as the need arises, how one can provide a list of lists to define a matrix. But let me now look at the matrix factorizations. So there are four important ones, and we will use the running matrix. We will use A to illustrate the LU factorization, the QR factorization. Both of them reduce to triangular form, the eigenvalue decomposition and the singular value decomposition. So I will work with subsections. So let me first do the LU factorization. So I have P, L, and U. So I will indicate what is the P. So the P is a permutation matrix. So one needs to interchange rows and columns to avoid singular matrices. Here you also see that the LU factorization leads to expression swell. And the most important thing actually is that P times A equals L times U, as you can see here. So the LU factorization leads to a permutation matrix P, a lower triangular matrix with the multipliers, and an upper triangular matrix with the upper triangular form of the matrix. So here one can verify this, that that here in this case P times A is actually not L times U. So let me try to fix this. So I have P times L times U. Still not the case. So there are still some permutations that need to happen. It might very well be that the permutation did not need to be applied. Oh yes, so here we are. P times L times U equals A. So that is the property. Okay, saved. So QR factorization is the second form. So 2.2, the QR factorization. And there is a QR, so here we had the LU operand, but the QR, the dot QR, will not work on this example. So we have to convert the matrix to the CDF type. So how do we do this? Well, I can select all the rows of this matrix. So here we are. And what I will do is I will build a list with numbers. A list of lists. So I will, on every number, I will apply, so the number, call it E, for E in a row, where for all rows in the A dot rows. So I practiced this and I'm quite confident that this will work. So here you see the numbers given of type complex double float. So this is the list bar of list representation, and now I make a matrix over, so it's also a 3 by 3 matrix, and I'm using the numbers in the list of lists. So this is a matrix of floating point numbers, and here now I can apply the QR factorization. The Q is orthogonal. I can look at this, but this is just a matrix of floating point numbers. So I can take the transpose times Q, and that will be the identity matrix. So you see that I have a matrix where the numbers, I have 0.99, so I have actually not really one, but you see up to the round off, I have the identity matrix. The off-diagonal numbers are less than the machine precision. Okay, so then the R is upper triangular, so let me verify this. So and I have that the Q times R equals the matrix C. Also the matrix A, but with round off. You see that this composition works. Okay, so these are the first two matrix factorization that reduce the matrix to an upper triangular form. Which one to choose? Well, if you are interested in numerical stability, then actually the QR factorization is preferred. That's also most likely the reason why we have to transform our rational matrix to the floating point numbers. So the third composition is the eigenvalue, the decomposition. So I can compute the list of eigenvalues directly on the matrix A. But observe that I will type that down because this is important. Observe that the eigenvalue decomposition, or the eigenvalues, are represented as QQ bar elements. So the question mark indicates that there is some uncertainty. So I will not go in there, but this allows to check the accuracy. So the eigenvalue computation is equivalent to the root finding problem, to computing all roots of the characteristic polynomial. So SageMath automatically converted to this symbolic numeric way of working, which is convenient. So let me illustrate now the eigenvalue eigenvector decomposition. So this goes via the computation of the right eigen matrix, and the right eigen matrix is a method that doesn't take A. So the matrix D is a diagonal matrix, and the matrix V, perhaps I can also show this, but the matrix V stores the eigenvectors of the matrix, and you can see they are normalized So the eigenvectors are up to a constant, and they are normalized such that the first constant, the first coefficient is 1. Okay, so what is then v times d if I take the product of the matrix of eigenvectors with the diagonal matrix. So the main point that I had to point out already is that obviously this is a diagonalization. What I'm trying to show now is that, let me write that down, is the factorization. We have shown that v times d equals a times v, and therefore we can write that d equals v inverse times a times v, or we can also write it the other way. We can write that a is v times d v inverse. So these are the diagonalizations that are defined by the eigenvalue decomposition, which is conveniently available in symbolic numeric computation, which provides us with a bound on the accuracy. Of course, one can also compute the norm of these differences. So that's another way of looking at it. So you see that all decimal places up to the question mark actually are identical. So all decimals before the question mark are therefore certain. Okay, so another diagonalization is the singular value decomposition. And this singular value decomposition is, again, not defined for the original matrix A. So we must use, again, the matrix C. So what do we have? We have an orthogonal matrix. So U transpose times U is an identity matrix up to the working precision. Also V transpose times V is the identity matrix. So these are just both orthogonal matrices. So for as an exercise, you can do U times U transpose. So multiplying matrices is not commutative, but for the inverses it is. Okay, you see that I generated a random rational matrix, but observe these singular values. So they go from 5 to 0.009. So the expression swell in this matrix could also have something to do with this. This last singular value is kind of the distance to the nearest singular matrix. How much should you change? So how large should the numbers be that you have to change the matrix C with, so that the determinant of the matrix is no longer different from 0, and your linear system no longer has a unique solution. So that's the geometric interpretation. So for symbolic computation, I should indicate the property that this indeed diagonalizes the matrix C. So it doesn't look like it, like these two matrices are the same. But again, looking at these numbers, we are now familiar with the scientific notation, and you see that the 10 to the power minus 16 is in double float precision very close to 0. So up to the working precision, we have a diagonalization. So these 4 statements, so starting with a matrix over the complex double field, these 4 statements here capture the essence of the singular value decomposition. Alright, so these were my matrix factorization over fields. So now I have still about 15 minutes to talk about matrices over rings. So over a ring, so we can think about integers, and let me make now another matrix a random matrix, now with numbers that I want of 3 decimal places, and the notation is rather strange. I want numbers of 3 decimal places. So that means that the lower bound is 100, the upper bound is 999. So I was trying to make somehow a snarky remark about the notation x and y, and that's why I made a mistake. So I had to look it up. So the parameters with the rational numbers are num underscore bound, then underscore bound. Here they are using the x and the y to give the bounds. Okay. With the greatest common divisor, you can introduce zeros, so I can compute the Hermite normal form of the matrix. So this is done with the method Hermite form, and I want to also see the U matrix. So let me check if I have that right. So the Hermite normal form is an upper triangular form, and the U is a unimodular coordinate transformation. So everything is integer here. Notice that we also have the expressions swell. So the matrix U is invertible, so the determinant is 1. So this means that so I have the U times A. The U times A equals the H. And because it is invertible, I can also see the A as the inverse of U times H. So these instructions that are represented here capture the essence of the Hermite form. So the Hermite form is a form that triangulates, so that brings the matrix to a triangular form. So there is also the Smith form, or the Smith normal form. The Smith normal form reduces the system into a diagonal form. And again, you see that this diagonal form, what is on the diagonal now, so in some sense we can complain again about the expression swell, but what is on the diagonal is actually the determinant of A. So it's also something that is characteristic of A. If you're going to compute the determinant, and perhaps I should make the point here, if you compute the determinant of A, well, here you see you have this large number. Okay, so then what is the property? The Smith normal form can be seen as a diagonalization. It's a diagonalization of the matrix where you can read off the determinant. So the determinant is typically the product of the elements on the diagonal. Okay, so this is in a nutshell matrices over rings, where we can triangulate via the Hermite form and diagonalize via the Smith normal form. So now I have still 10 minutes left to indicate the applications to resultants. So with resultants, we eliminate variables, similar like we did with the construction of the Gröbner basis. Now, again, the main purpose of this lecture is to give an overview of what is available in computer algebra systems such like SageMath. Defining resultants would take some while, but I hope that one gets the flavor. So we consider a polynomial ring P. So this is a polynomial ring, and over the rational numbers, and I will generate two random polynomials. So one I call little p, so a random element of degree 2 and with 5 terms. So that will be my first polynomial. See, it doesn't really look that random, but it's random enough for us. So I will make another polynomial, also with 5 terms. Well, I want 5 terms. Let's see what I get. I get 4 terms. So these two polynomials define a polynomial system in two variables. I can reduce this to an upper triangular form by viewing these polynomials as polynomials in x with coefficients in y. How do I do this? Well, I can compute the resultant of p with respect to q and eliminate the x, or I can compute the resultant of p of q with respect to p and also with respect to the variable. And you see, up to a sign change, I have the same polynomial. Okay, what's the connection now with the matrices? That's the last thing that I would like to show. One can define the Sylvester matrix. So the Sylvester matrix is a matrix that will define the resultant, essentially. So the determinant of the Sylvester matrix will be the polynomial that I just computed. So let me make the point. So the determinant of S is that polynomial of degree 3. So what does that give me? Well, I have a triangular form now. So let me put everything. So this is again a very short introduction. So everything fits in one short screen. So I have defined two random polynomials. And if you look at these polynomials a little bit more carefully, then you see that the first polynomial p is linear in x. So the polynomial p, you can solve for x. So you can express x as a function of y. You have to divide by y. But you can get the y values from solving this polynomial, which is the resultant. And I have the resultant now given 3 times, once with this resultant method that is defined on these polynomials of the library that come from singular, or I can compute it explicitly via the determinant of the Sylvester matrix. So observe that I have reduced with essentially one computation so jointly, so let me document this. So jointly with P, the determinant of S, determinant of the Sylvester matrix, defines a triangular form for the system defined by P and Q. So resultants are very convenient to selectively eliminate variables. So Gröbner bases are a bigger machinery and more general, richer, but resultants are still very useful to selectively start eliminating variables. And the point, the relationship with linear algebra, is that we are computing a determinant of matrices of polynomials. So we can't divide polynomials, but nevertheless, with the same technology that works for the matrices over the integers, we can compute the determinants. Okay, so this was a very quick overview, and I hope this is interesting, and I hope you can see that computer algebra has a lot to offer in the study of linear algebra. So I should have said right from the start that linear algebra is very well represented in scientific computing, for which packages like NumPy and SciPy are appropriate, which we also will use in SageMath in a later lecture. But this gives a view of linear algebra, which is much closer to the mathematically numerical fields, which is more extensive than just computing over the hardware doubles. Okay, I'll stop the recording now, and again I hope that this was an interesting lecture.